one final example of an improper integral. And this is probably one of the more difficult ones that we're going to work through. We have our negative infinity to positive infinity, dx, e to the x plus e to the minus x dx. All right, or I'm sorry, dx over e to the x plus e to the minus x. A number of reasons why this is difficult. Number one, it doesn't necessarily have discontinuities except for the infinity, so we're going to have to break it up into two integrals. But the integration of this is really sneaky, especially if you haven't necessarily tried this technique before. So let's start this by breaking it up into two separate integrals. So we're going to have our limit as c approaches negative infinity from c. I like 0, okay, but you could use whatever number you want. Dx e to the x plus e to the minus x, right? Plus limit, and I'm going to use d approaches infinity. And let me make that look like a real, some sort of English structure. So lim as d approaches infinity of 0 to d of the exact same thing, dx over e to the x plus e to the minus x. All right, now let's just worry about the integral by itself, and then we'll come back and we'll do all the limit and all that good stuff. This is going to be the integral of, let's just say, dx over e to the x plus e to the minus x. Now, this is a sneaky integral to be able to evaluate. And certainly, if you plugged it into Wolfram Alpha, it would tell you what the answer is. All right, but let me show you how to get to the answer, because that's even more important. So what I'm going to do, and this is something you might not think to do, but I'm going to factor an e to the minus x out of the denominator. If you do that, that's going to turn into e to the 2x plus 1. All right. And you might be thinking, well, why would I ever want to do that? All right. And by the way, if you don't trust me, just distribute that e to the minus x back through, and you'll see that you get back to the original integrate. Well, what we could do is we could just move this up to the denominator. Okay. And if we do that, then we end up with an integral of e to the x dx divided by e to the 2x plus 1. If we judiciously choose our u, this is a u subproblem. Let's let u be e to the x. Du would be e to the x dx, which is precisely what we have here. And wouldn't that mean that u square would be e to the 2x? And so what we would end up with is an integral of du over u square plus 1, which is precisely arctan of u in this case. All right, so that's the integral of our du over u squared plus 1. All right, but we don't want arctan u, and of course it's arctan u plus c if it's indefinite, but remember we have to go back up here and do the definite stuff. And so this is going to be arctan of e to the x, since u was e to the x. All right, so we're going to substitute that back in for this integral as well as this integral because we've evaluated. Okay, so we get limit as c approaches minus infinity, all right, of our arctan of e to the x, and that's going to go from c to 0, plus the limit as d approaches infinity of arctan e to the x from 0 to d. All right. Now be careful with this one, because when we substitute 0 back in, it's going to be e to the 0, which is not the same thing as 0. Okay, and then the same thing with the infinities. Okay, so we have to be really careful with this one. That's why this one's a lot tougher than some of the other ones. All right, so by substituting back in, we get limit as c approaches negative infinity. Let me make that look like real negative infinity. Sorry. of arctan of e to the 0. All right, so remember e 0 is first. All right. Minus arctan of e to the c. All right, so that takes care of that one. All right. And then we have to substitute plus, where we take the limit as d approaches positive infinity. Now this time d is going to be the upper bound. So this is going to be arctan of e to the d minus arctan of e to the 0. All right. Now, some good news, if there is any good news. I want you to notice that we have a positive arctan e to the 0 and a negative arctan e to the 0. All right. Those are going to cancel each other out. All right. So that helps out. And by the way, arctan of 1 is just going to be pi fourths. So in reality, this just becomes pi fourths minus pi fourths, which are going to cancel each other out. If we take the limit as c approaches negative infinity of arctan, okay? And so this is really going to be e to the c. And remember, this is negative infinity, right, guys? So what's going to happen with this is it's actually going to go, if we substitute negative infinity back in here, this is actually going to become 1 over e to the infinity, which is going to be arctan of 0. Okay, so when we substitute these back in, we have to be careful, especially with our arctan stuff. All right, so this is going to be, like I said, 1 over e to the infinity, which is going to be 0. Okay, so by substituting that back in, that becomes minus arctan of 0. Okay, because e to the minus infinity is going to be 0. But then when we substitute regular infinity back in, that becomes e to the infinity, which is infinity. Okay, so we get minus arctan of 0 plus arctan of infinity. Looking at the graph is going to be helpful. All right, and I think we did this a few problems ago when we looked at the graphs of the arctan function. But just to remind you guys that this is what our arctan function looks like. All right, it's horizontally asymptotic at negative pi halves and pi halves. And so arctan of infinity, or as it approaches infinity, is going to be pi halves. Arctan of 0 crosses directly at the origin, which is 0. So ultimately, this really just becomes pi halves. All right. And if you don't believe me, what you could do is you could just throw it into Wolfram Alpha. All right. And I actually did that right here, okay, just to kind of expedite our process for this. And when I typed it in by using like the manual way, it didn't work. So I'm just going to go ahead and execute this. Hopefully it's a little bit faster than what we did before. And I want you to notice right here, it gave us pi halves, which is precisely the value that we just got before. Okay, so now, of course, on your examination, you have to make sure that you understand how to do this sort of process. If I were to ask you how to go through and do one of these sorts of improper integrals, okay, so be wary of that, okay, not just being able to plug in the answers, but also and getting them out of Wolfram Alpha or some sort of computer algebra system, but making sure that you can do all this by hand. All right, so this is the last section that we had, not only for improper integrals, but also for techniques of evaluating integrals. So our next big section that we're going to look at is all going to be applications of integration. Okay, so, but for now, make sure you can go back, make sure you can understand all the different techniques that we use to evaluate these improper integrals, as well as any integral up to this point.